BC Calculus, lesson 2.3, continuity. I apologize in advance. Something happened to my voice, so I'll do my best. How do we define a continuous function? No breaks. And by breaks we mean no jumps, holes, or infinities, vertical asymptotes. So why do we care? That's a great question. I don't have a great answer for it. I'll touch on it a little bit later when we do the intermediate value theorem. But long story short is, once we know it's continuous, we can do calculus to it with no reservations. We don't have to worry about certain points on the graph. And for hundreds of years, most people thought that all functions were continuous and they didn't even get into it. Then they realized there are many things that are very discrete in the world. If you look in the field of chemistry, you'll see lots of things that, it jumps from one, what do they call that, atomic structures from one level to another. There's nothing continuous about it. So anyway, an example helps here. When is the following graph continuous? From 0 to 1, it's continuous. Then it jumps. From 1 to 2, it's continuous, but then there's a hole that's been filled in from 2 all the way to 3. So if you said, when is this graph continuous, I would get to say from 0 to, looks like 4 out there. And then I would say except at, and these are the points, x equals 1, 2, and 4. So that's just an example. We use more to get there. Got a definition. Generally speaking, the AP curriculum is focused on interior points. They're not going to get too hung up on the exterior points. But we make this exception so that people don't get freaked out by it. In an interior point, if the limit is equal to the actual value itself, it's continuous. If on the exterior point, at that point, the limit from that side is equal to that point, so you get this little plus and minuses in there, then you're good to go. Much more on this later. I would actually, I've read up, found some other spots. Does a limit exist? And yeah, sure. Does the function exist? My pen's giving me a hard time, so I apologize. And then, does the limit equal? Answer all 3 yeses. You've got a continuous function. Doesn't have to be perfectly smooth, could be very jerky, but yes, it's a continuous function. So if it's not continuous at a point C, we say it's discontinuous at C. And note that C need not be in the domain. For example, let's just do y equals 1 over x. You would probably say, oh, it's discontinuous, obviously, and you'd be right, discontinuous at x equals 0. And other people would point out, well, wait a minute, it's not even defined at x equals 0. If I say what's the domain of this thing, that's going to come up more in a minute. We'll talk about that, and it's very confusing, but it will make sense eventually. So find the points of continuity and the points of discontinuity on the GIF function. Hopefully you remember the GIF. I don't like to draw too many steps of it. It's what I call a rounding down function. It just chunks everything down. Boy, I really didn't even come close to getting this to scale, did I? And interestingly enough, what's the domain? All reals. You could write it as negative infinity, infinity, since we're really using interval notation more often. But it is discontinuous. You could say it's continuous from negative infinity to infinity, except at all integers. So every time you hit an integer, it jumps. More and more and more on this as we go along. What are the types of discontinuities? Well, I just showed you one. Jump. I'll draw a picture in a second. Infinite or essential. I've seen this written a couple different ways. We have a whole, which we call removable. So let's get let's write that down. Removable is just a pure whole. A jump has a couple different versions. Let's draw on some graphs. So jump could just be coming along and then bang, up it goes. Just keeps going. But it could also be one of those ones with a hole in it that the hole is up somewhere else. At that point, it's defined differently. Infinite or essentials, just asymptotes. And the removable looks like the jump, except there is no replacement. So we could just say, well, at x equals 2, we'll fill that one in. There's one other. I'll draw the rest of it in a minute. It's what we call oscillating. We can't actually even finish it. I believe sine of 1 over x is like this. As we get closer and closer to 0, it just keeps going up and down. I believe you have a homework problem like that, either already have or will, so it'll give you a good example there. Now, I talked about this briefly earlier, and it is confusing. Is y equals 1 over x continuous? And you would have to say yes, it is. And people would say, well, what about at x equals 0? And I would say x equals 0 is not even in its domain, so you do not get to consider that. So then you could ask a different question. Is it continuous on this interval? And then it would be no, because at x equals 0, there's a infinite discontinuity. Very confusing. So a function can be continuous because we're defining it over its domain, but then if I give you an interval, say, well, yeah, and remember we noted that before, the point C may not even be in there. So just because you were dying to know, algebraic functions of continuous functions are continuous. So if f is continuous, g is continuous, then add them together will be continuous. So are composite functions. If f is continuous, f dot and g is continuous, f dot and g will be continuous. And you can play with all these. Make sure you're never dividing by 0, otherwise you're pretty much good to go. So let's do a composite one. Let's make f of x equal the absolute value of x. G of x is everything else here. I know the absolute value is continuous because it just comes down and goes up. And I know x is continuous, sine of x is continuous. X squared plus 2 is continuous, even though you look at it, whoa, there might be something on the bottom. We can't get a 0 on the bottom. So then we would say f and g are both continuous, therefore f dot of g, which equals is continuous. Not really a big deal, but just something of interest. And now, just a strange sounding theorem that's important, called the intermediate value theorem. And this is what we're getting at with continuity. Things are continuous. Hey, I know something's continuous. All right, I've got a curve, and it's continuous from A here to B. So this would be f of A, and this would be f of B. If it's continuous, then I know that every value is hit between those. Every value of f of A and f of B will be hit somewhere between A and B. That means we have just one clean curve. And this theorem is one of those ones where you're like, well, duh, obviously, but without it, we cannot make the statement about continuous functions. Two functions that are not continuous, if I give you the interval, are the greatest integer function, which is not continuous at all, and then something like y equals 1 over x, which is not continuous if I say define it over an interval that includes 0. So the intermediate value theorem says things like, is any real number exactly 1 less than its cube? So we graph this on our calculator, and we get something like this. Because what we're doing is saying, is any number x equal to its cube minus 1? And we do some math. Get x to the third minus x minus 1x equals 0. Well, all the values exist there. It might not be a clean number. It might be irrational. It will not be imaginary. But by the intermediate value theorem, we can say yes. And we're not actually finding it. If you needed to find it, what I would strongly recommend doing is finding the 0 by using your calculator and using the intercept, the 0 button under calc. So that is it. Go do some problems. You got plenty to keep you busy. Happy mathing.